All right, today we're going to talk about a really clever piece of internet architecture called consistent hashing. Now, on the surface, it's this beautifully elegant solution to a massive, massive problem. But as we're about to find out, that elegance, it hides a pretty catastrophic flaw.
Okay, so just imagine this for a second. You're building the next big thing, right? You've got millions, maybe even a billion users. Every single time one of them logs in, you have to grab their data, instantly. So how in the world do you spread all that data across a bunch of servers so that it's fast, it's efficient, and crucially, the whole system doesn't just fall over when a machine goes down? That's the big question we're digging into.
Well, the answer engineers came up with is this really, really smart concept called consistent hashing. And I mean, it's a method that seems pretty much perfect for handling data at a scale that's hard to even wrap your head around. So, let's break down how it actually works.
At its heart, consistent hashing is really just a clever way of dividing up work. The whole point is to spread data, or really any kind of load, across a whole bunch of servers. And its big claim to fame, its key feature, is that when a server gets added or, suddenly dies, it's supposed to only affect its immediate neighbors. It's meant to keep the chaos to a minimum. At least, that's the theory.
Okay, so to really get this, you don't need a bunch of complicated diagrams. All you have to do is picture a giant imaginary circle, kind of like a huge empty clock face. This circle, or ring as they call it, is the absolute foundation of this whole system.
And look, when I say massive, I really mean it. This circle isn't just some drawing. It's basically a gigantic number line that's been bent into a loop. And the points on it range from 0 all the way up to 10 to the 18th power. That's a 1 with 18 zeros after it. It's just an unbelievably huge space of possible values.
Okay, so we've got our ring. What's next? Well, we need to place our servers, we'll call them nodes, onto this ring. And the way we do that is with something called a hash function. Think of it like this. You take a server's name, say node 2, you feed it into this function and it spits out one of those giant numbers, which gives that server its own unique spot on the circle.
All right, our servers are on the map. They have their spots on the ring. But now, the big question. How do we figure out which server is responsible for which user's data? This is where the real genius of this whole setup kicks in. It's actually a pretty simple three-step dance. First, you take a user's ID, and you do the exact same thing we did with the servers. You hash it. That gives you a number. Second, you find where that number lands on our big circle. And then third, and this is the key to everything, you just start moving clockwise around the ring from that user spot until you hit the very first server you see. And boom, that server is its home.
So let's make this less abstract. For example, after we hash their user IDs, maybe Dion and Africa both land on points on the ring where, if you go clockwise, the very next node you run into is node 2. So node 2 gets their data. Same thing for Freddie and Trishtika. They might hash to spots where the next server in line is node 5.
And that's basically it. See? It's so clean, so logical. Every user has a home. The load gets spread out across the servers. Everything seems perfectly balanced. It's a really beautiful design. I mean, what could possibly go wrong?
Well, it turns out that this super elegant system has a hidden fatal flaw, a real Achilles heel that can take one tiny little hiccup and turn it into a full-blown system meltdown. Yeah, this is where the story takes a pretty dark turn.
Look, servers aren't perfect. They fail all the time. They go offline for maintenance, they crash. It just happens. In any big system, you have to plan for this. It's totally expected. But the question is, what does our beautiful, elegant hashing ring do when one of its nodes just vanishes?
So let's walk through it. Let's say node 2, the one that was handling data for Dayan and Africa, suddenly goes offline. Poof, it's gone. But according to the rules of our system, Dayan and Africa's data still needs a home, right?
So what happens? Well, we just follow the rule. Travel clockwise to find the next available server. But with node 2 gone, when we start from Dayan and Africa's spots on the ring and move clockwise, the next server we hit is now node 5. And just like that, suddenly node 5 isn't just handling its own users anymore. It's now also responsible for every single user that belonged to node 2.
The impact is immediate and it is brutal. The workload on node 5 instantly doubles. I mean, 1 second it's just chugging along with its normal amount of traffic, and the very next second it is drowning under twice the load. That's a huge, instantaneous shock to that server.
And this is where things get really dangerous. Because that sudden shock, that doubling of the load, isn't just a temporary problem. No,
It's the trigger. It's the first domino in a chain reaction that's about to ripple through the entire system.
I mean, think about it. Servers are built to handle a specific capacity. If you instantly double that capacity, it's just a recipe for disaster. There's a really good chance that Node 5, which was never meant to handle that much traffic, is going to buckle under the pressure and fail, too.
So what happens when Node 5 dies? Yep, you guessed it, the exact same thing. All of its original traffic, plus all the traffic it just inherited from the dead Node 2, now needs a new home. And following our simple clockwise rule, that entire, now massive, combined load gets dumped onto the next server in line, Node 4.
So let's be clear, Node 4 is now getting hit with its own traffic, plus Node 2's traffic, plus Node 5's traffic. Its load didn't just go up a little bit, it has tripled, instantly. The odds of Node 4 surviving that kind of hit, they're basically zero.
And this is the terrifying conclusion. Because when Node 4 inevitably dies, its now tripled load will just move to the next server, which will fail even faster, and then the next, and the next. This is what engineers call a cascading failure. One single, tiny fault that triggers a complete and catastrophic system-wide collapse.
So what we're left with is this incredible paradox, right? We have a system that was designed with such elegance, such simplicity, specifically to handle servers failing gracefully, and yet that very design contains the seeds of its own total destruction. It's a powerful reminder that in these incredibly complex systems, the most dangerous problems, they aren't always the obvious ones. Sometimes they're hiding right there in plain sight, baked into the very logic of the design.